Hello everyone, this is unit 4, part 2, AICE physics review. This is like moments around the pivot, as well as like other stuff. Don't forget to subscribe. Yeah, without further ado, let's get into it. So A is define a moment of force. So a moment in force, you kind of have to like memorize the definition. If you do enough past paper problems, you will eventually just memorize it. But in this case, the moment of force is just going to be the force times, or it actually should be a little bit more specific. Although it is the force, it's a perpendicular force. Force times times the distance between the pivot and point of force. Yeah. So for B, an arrangement for lifting heavy loads is shown in figure 4.1. A uniform metal beam AB is pivoted on a vertical wall at A. The B is supported by a wire joining end B to the end of wall C. The beam makes an angle of 30 degrees with the wall and the wire, making an angle of 60 degrees with the wall. So it is going to be a right triangle kind of. The beam has length 2.8 meters and a weight of 500 newtons. A load of 4,000 newtons is supported from B. The tension in the wire is T. The beam is in equilibrium. Okay, so a lot of information. By taking moments about A, show that T is equal to 2.1 kilonewtons. I'm pretty sure. Okay. So in order to find T, we know that T is actually going like quote unquote upwards, while in B the load and the weight of the beam pull it quote unquote downwards kind of in a motion. So if you actually like draw this out, something like that, probably, we can see that this angle right here should be either 30 or 60, and you have to figure out which one it is. But if we for example draw this, complete this triangle here, got that this is 60 and this is 30, so then this is 60. So let's do the load first. So the moment of the load is going to be the length of the beam, which is 2.8 meters, times the weight, right? The weight of it going down, but it has to be perpendicular to the beam, right? So in this case, it's going to be on this side. Sorry, it's kind of hard to see. But on BD, we have to calculate this. So we know our hypotenuse is going to be our 4,000 newtons. So it's going to be 4,000 newtons times cosine of 60 degrees, because it's right next to it. We're looking for this side here. Likewise, for the weight of the beam, it's going to be halfway through. So it's going to be 1.4 meters times 500 newtons times cosine of 60, because it's going in the same direction. So now if we use a calculator, we see that if we add these together up, it's going to be around 2.1 kilonewtons, rounded to the nearest 2 sig figs. And we know this is true because the sum of moments clockwise is equal to the sum of anti-clockwise moments. And we know that these load and weight are equal to clockwise, and the anti-clockwise is just t. So then if this side is 2.1, so is t. Okay, so calculate the vertical component TV of the tension T. Okay, so our tension is going like this, where our angle with the wall is 60. So then this is 30. And thus our component is sine of 30 degrees times our magnitude, which is 2.1 kN, which is about 1.50, I think, newtons. So it's around 1100 newtons. State and explain why TV does not equal the sum of the load and the weight of the beam, although the beam is in equilibrium. It's mainly because the wall exerts a force on the beam also, which added to TV is equal to load plus the weight of the beam. A light rigid rod XY has an object of weight W fixed at one end. The rod is in equilibrium, resting on roller Z and the vertical wall at X. The roller exerts a force R on the rod as well. The diagram shows the directions but not the magnitudes of the forces R and W. What is the direction of the force on the rod at X? Okay. So this is we have to look at the moments or the vertical components and see if they cancel out, kind of. And one way to do that is to actually assume that the wall does not exist, for example. So if the wall does not exist, we have this functional R, right? And then we have our weight here that goes down at W and has some moment force perpendicular to this. So since it is going in that direction, we should have a force that that neglects this downward force. So then say like this is our answer, right? Our first component of this force should also be in this direction, just to negate it. And then we have a force that goes upwards here, which also means that it's going this way. So our answer is just going to be D. Three coplanar forces act on an object in the directions shown. Which diagram could the object be in equilibrium? So we have A, B, C, and D, and they all have different free body diagrams of different forces going in different directions, different magnitudes. Let's try and break this problem down. So equilibrium means that the force, the resultant force is equal to 0, as well as the resultant torque. But it's not necessarily, I don't think we can see like torque here. just know that it's implied. So then since the force is equal to 0, we know that the x and y components of each of these should also be equal to 0. And we just need to find one that suits these criteria. So we look at D, for example. We can see that these two forces go in opposite directions and they have roughly the same magnitude. So then those cancel out, but then we have an extra force left. So that means the sum of the force is not equal to 0. And C, we have this force here as well as this force. However, they may not look entirely equal. It is plausible that they're kind of the same magnitude. And in terms of vertical components, they are somewhat canceled. So let's look at B. This C might be a viable answer, but we have to look at B. So we see that B goes left, left, but then there's a right, down, up, up. So it turns out that it's not necessarily in equilibrium because we have these two big magnitudes of vertical component going up and one small magnitude going down. So B is not in equilibrium because this condition is not necessarily satisfied. Let's draw the vertical components of this. So turns out this one does make kind of sense. The problem is, I think, that there's too much vertical force vertical force happening, because you can see that like these two are roughly equal magnitude as well as this upward force, so not necessarily A. So then we're left with C. Another reason why C is like somewhat viable is because since this is at an angle, the vertical component is not necessarily the same as this vertical component, and this small vertical component on the right kind of makes up for this smaller one. What is the center of gravity of an object? So when it comes to like these definition problems, in general, you should try to think about it on your own, have an idea in your head, and the idea in this question should be that the point where all gravity exists, or where gravity acts on an object. Because it turns out that gravity doesn't act on like all parts of an object, and it acts on the center of gravity. And it turns out that if we look at these, you see that B immediately pops at it. It can be D, where gravity acts on an object. But the thing is that like my definition is a little bit imprecise because comparing weight versus gravity. But if you look at a free body diagram and you see this, you see that the units is actually in newtons. So then this is actually talking about weight, not acceleration. So yeah, I hope that makes sense. An air conditioning unit is supported by a rigid beam PQ as shown, which diagram shows the directions of the horizontal and vertical forces acting on the ends of the beam. Okay. Okay, so we have to consider both the wall and the air conditioning unit. So we know that there should be a force going down because the air conditioning is obviously like pushing down on it. And since this is going down and the beam is not experiencing any emotion or motion, it should also have an opposing force up. We should also note that there is like kind of like a moment going on. Which kind of just like presses the beam on itself. I think that's how you describe it. Because this force going on it is like this, right? It's going in the direction of this way. So then this is made up of two components, like that. And thus the wall should also just cancel out those components. So I believe the answer is B. A sphere is acted upon by various forces, all the same magnitude. Which system of forces provides a resultant torque but zero resultant force on the sphere? Okay, so we want resultant torque, but we want zero resultant force. So let's go by each one. So A here, we see that it goes up, up, and down. That means that there's 2F up and 1F down. So resultant of F is not equal to 0. That's not A. For B, it's the same thing as F. I meant A. There's 2 going up, 1 going down, so it's not necessarily. So for C, we can see that there is no resultant force, but there's no resultant torque. As you can see, it's like just gonna stay in motion or just like move at a constant space, constant motion. So like there's no resultant torque, so it's not D. I mean not C. So then our final answer is gonna be D. A uniform horizontal footbridge is 12 meters long and weighs 4,000 newtons. It rests on 2 supports X and Y as shown. A man of weight 600 is at a distance of 4 m from support X. What is the upward force on the footbridge from support X? Okay. So let's try and label our distances. $8 meters, and then we have a weight that goes from the middle, which is 4,000 newtons. What is the upward force of the footbridge from support X? So it turns out that we can just take moments from this, I'm pretty sure. So we can take moments to support our answer. So we have that Y is going to be acting as our pivot. So then we can have the sum of anti-clockwise and clockwise. So clockwise in this case is going to be equal to force of X, right? Force of X times 12 meters. Anti-clockwise is the weight of the human, which is 8 meters times 600 newtons, plus the weight of the drawbridge, which is 6 meters times 4,000 newtons. So 12x newtons is equal to 480 plus 24,000. If you divide by 12, this is 400, and this is 2,000. So then X is equal to 2,400 newtons. A uniform beam of mass 1.4 kg is pivoted at P as shown. The beam has a length of 0.6 meters and P is 0.2 from the end. Loads of 3.0 and 6.0 are suspended. 3 point blah blah blah. Lengths away from the pivot. What is the torque that must be applied to the beam in order to maintain it in equilibrium? So given that these are non-zero values, we can say that the clockwise and anti-clockwise are not equal, and so then we have to find the difference between these two numbers, or the absolute value of these two numbers. So we can try and calculate it. So clockwise motion turns out it's going to be this one, because once you draw the free body diagram kind of force of direction, this goes in the direction of that way. So it's going to be 6.0 kg times 9.81 meters per second squared. Because this is in a mass, we need to include the gravity in order to make sure that it's a force and we're actually dealing with the right units. And it turns out this is like 58.86 newtons. And then the sum of anti-clockwise is equal to 3.0 kg times 0. I forgot to do the distance, but for moments you have to account for the distance. So you have to multiply this by 0.15. Which is 8.829 Newton meters. And so now this is 0.3005. And we take the positive. We take the positive difference of this. And it turns out that we get 1.4715, which is neither of these answers. Great. So it turns out we didn't get the answer. So let's try and troubleshoot. So okay, so my mistake is that I actually forgot to account for the weight of the beam. So we have to redo one of the calculations. The weight of the beam is on the left side of the pivot and goes down, so it's included with the anti-clockwise thing, anti-clockwise sum of moments. So then we have 1.4 kg times the distance. So we know that the length of the entire beam is 0.6. Half of that is 0.3. And since the pivot is 0.2, this distance is 0.1 meters times 0.1 meters times 9.81 meters per second squared. And you have to do this math as well. Which makes it 11.67, and then you have to subtract that by 8.829, and then you got 2.8 Newton meters, which is D. A fairground ride consists of 4 carriages connected to a central vertical pole. as shown in the following view from above. A motor rotates the center pole around its axis. This results in 4 carriages, each moving along a circular path. The distance from the middle of each carriage to the center of the pole is 3.2 meters. When they are moving, each carriage experiences an air resistance force of 85 newtons. Assuming there is no other significant resistive forces, which torque does the motor need to apply to keep the system rotating at a constant maximum speed? Okay. So it turns out that the distance between each of these is 3.2 meters, and they all experience a force of 8.50 newtons. So then the moment of each one is 3.2 meters times 85 newtons times the 4 carriages. Which turns out to be equal to 1.88 newton meters, and to 2 sig figs is 1.0 newton meters. So the torque is then D. A car of mass m travels at a constant speed up the slope at angle theta to the horizontal as shown in the diagram. Air resistance and friction provide a resistive force F. The acceleration of free fall is G. What is the force needed to propel the car forward at this constant speed? So if we draw this diagram, this is mg and this is theta. So we want this resultant force, we'll call it just like our answer, F answer, sorry. Our F answer is equal to the resistance force, why do I just keep thinking it's R, plus the gravity force. So F answer is actually equal to F plus mg times sine theta, because it's the opposite side. And then wow, it's actually going to be D. Okay, so that is the end of Unit 4, Part 2, AICE Physics Past Paper Problems Review. Thank you for watching. If you made it this far, don't forget to subscribe.